So I'll make sure I keep us on time. I only have 9 slides. I'm sure that I can pretty much slide it in under 15 minutes. So my name's Roman Gomez. Happy to be here. Almost feel like I'm at an AA meeting. I'm just joking. So when I first came to Rice, I came here studying dark matter and did my first 4 years. I didn't go to SPAC immediately, but I got here as fast as I could. And thankfully, when I started working for Dave, he introduced me to an interaction cross-section that was much more favorable than dark matter. So I'm currently working at Southwest Research Institute, work with plasma instrumentation. Again, something I carried on from Dave Young as my thesis advisor. And so we're going to talk about a mission that we recently won, actually, during the pandemic. It's for a new solar wind sensor that will be placed at L1. Next slide, please. So this instrument has heritage with an instrument that was used on the Comet Chaser mission, the Rosetta mission. And in that original incarnation, it was used to survey both ion and electron populations that were coming from this comet, 67P, because I'm not going to say the Russian name. It was very difficult to pronounce. So the way it worked is you have 2 sensors, and as Hugh was talking about salad bowls earlier, you can see that we use salad bowls quite a bit in our designs. Electrostatic analyzers are, you apply an electric field between 2 electrodes. One of them is usually held at spacecraft ground, and then you apply voltage to the other, and the field between those plates corresponds to an energy to charge ratio of particles. So this allows you to, in a very careful sense, survey the ion populations and capture what is known as the velocity distribution function, which is the holy grail for plasma guys. That's basically the closest thing we can get to an actual knowledge of what the plasma is doing. So we kind of just parcel it in energy and angle. Now, in the case of Rosetta and in the case of the SWIFO L1 instrument, which is going to be launching along with the IMAP mission, which actually is tasked with measuring the composition of the interstellar medium, we have to be in a fixed orientation. And of course, as I said, we wanted to capture this velocity distribution function, so you've got to see the plasma in its entirety. But sitting on a fixed instrument or sitting on a fixed spacecraft is not going to afford you that. And my first project working at Southwest Research was with the MMS mission, which are spinning spacecraft, no optical instruments, so I was a spoiled brat because my instrument was working on a platform that it was intended to work on. It allows, a full field of view. In this case, I'm not going to be able to get a full field of view of the plasma, so I've got to find a way to make it more visible to me. So in addition to having the electrostatic analyzers on the inside, I have a set of electrostatic analyzers on the outside as well, which are deflectors. And again, you apply equal and opposite voltages to those. And depending upon the magnitude of the voltages, this allows you to very carefully and stepwise sample a much larger portion of the velocity distribution function or of the plasma population than you would normally otherwise be able to on a fixed spacecraft. Next slide. So again, how does it work? Again, applying different voltages to these deflectors allows you to increase your field of view. Now, as I pointed out earlier, when we had IES Rosetta sampled both ions and electrons simultaneously. On the SWIFO SWIPS instrument, its primary mission is to measure solar wind, measure the velocity, measure the moments, and give an idea, an early warning system for space weather, right? Because we are so dependent on satellite communications and things of that nature, and we'd really like to know when things are going to go bad for us. So that's the point with this instrument. So the idea then is to use 2 ion sensors. Now, we're going to have one, the bottom sensor is going to be our primary. The top sensor will be our secondary, and it will also allow us to make periodic calibrations, because you always want to make sure that you have your microchannel plates working and saturation. If they've degraded a bit, then you want to go ahead and bump up the voltage so you can account for that loss and gain. So that is the idea. So we are looking at measuring from 16 eV to 160 eV to 32,000 electron volts. 32,000 electron volts is equivalent to a proton moving at approximately 2,500 kilometers per second. So we're looking at fast solar wind. Granted, average solar wind properties, these things are moving about 400 kilometers per second, but you do have these situations where you get high-speed solar wind. Again, we're using the deflectors to scan out of the ecliptic, so we're using those to scan above and below. And then we have a series of anodes, fine 5-degree and a couple of gross 10-degree anodes that cover a 90-degree swath. And then again, that allows us to resolve the angular distribution of the solar wind. Next slide. So when I was 18 years old, I was an infantryman in the United States Army. And we were playing war games, and I got to play the bad guys. Back then, it was the Russians, right? So we were supposed to ambush elements of the 7th Infantry Division, and they never showed up. This is 1989, right around St. Patrick's Day. And I think a lot of you would remember what happened then. Now, again, I was a young 18-year-old who just happened to be slightly well-read. So as I'm laying on my rucksack, waiting for these guys to show up, and they never showed up, I look up in the sky, and I see these lights shimmering back and forth. And, I was really amazed at this. But I realized that I'm in northern Florida, and that I really shouldn't be seeing the aurora borealis where I was. But sure enough, as we know, a really big event hit us. I think a CME along with an X-class solar flare was kind of like a perfect storm of space weather. And I think, if I'm not mistaken, I think Quebec had a really bad problem with their power grid, and all because of the currents hitting ground. This is exactly what we are keyed for here. This is what we're looking for. We're going to be working in conjunction with coronagraphs, magnetometers, and again, providing an early warning system for events such as these CMEs, CIRs, high-speed flows. And, one of the things I'm really happy about is throughout my entire career, I've always been asking, what does the velocity distribution of the solar wind look like? Because, if you ask anyone, well, you can't get that. Or if you go and you look on your primary data, not Inspires are for proposals, but I'm trying to remember the CDS. I can't find them anywhere. But now, on the plus side, I'll be able to build an instrument that directly gets them, and I'll be able to, acquire those things. And if anyone ever asks me, well, do you have any samples of a solar wind velocity distribution? I go, here you go. Next slide. So again, as we pointed out, we're going to be making measurements in real time. We have a 1-minute cadence. So we're going from this 160 EV to 32K EV in 128 logarithmic steps. And we're doing that, again, I think we're covering plus minus 22.5 degrees, so 45 degrees above, 22.5 degrees above and below the ecliptic, and then 90 degrees across. We're doing that, again, in 1 minute. Give it as approximately as real time as possible. And again, to indicate, when we have high solar wind events, CMEs, solar flares, and the like. Next slide. So, what are we supposed to do? Well, we're going to be measuring plasma ion velocities from 200 to 2,500 kilometers per second, have 10% accuracy in all of our primary measurements, a really large range of plasma ion densities, 0.1 to 150 per centimeter cubed, and then the thermal plasma ion densities with, using our energy and angular range. And a rather large swath of temperatures from 40,000 to 2,000 Kelvin. Yes, sir.
Wasn't the sort of nominal solar wind velocity about 400 kilometers?
Yes, sir, about 400 kilometers per second. And that's the thing, we're really trying to focus on some of the extreme events. We want to make sure that we always are able to capture the nominal events.
How much variation from that do you see, just roughly?
So, looking at, I think it was Gosling's paper. Gosling actually has an average of 368, but 95% confidence takes you about to 750 kilometers per second.
Wow.
So we can still, we'll still be able to get that measurement rather reliably. Again, the big thing is, can you get those high velocity events? And that, again, that's what this was meant for. I think a lot of people understand that the majority of the times when you're measuring solar wind, a lot of that is done with Faraday cups. Faraday cups are really good because they can handle an extreme amount of flux, but the only problem is that you can't get as high an energy. I think they have what's known as an analyzer constant, which is unity gain. So you can only go up to, say, 1,000 volts. You can't go very high in space. Between the plates, we're supposed to be, that's a 1 millimeter gap. We're looking at putting almost 4 kilovolts between those. And yeah, most people, exactly. But preliminary testing with the EM has shown that we so far have been able to apply those voltages rather reliably. It's funny, and kind of digressing here again, I pointed out that the first plasma instrument I worked with was with Dave, the hot plasma composition analyzer of the magnetospheric multiscale mission. In terms of a plasma instrument, this instrument has a field of view like a grouper eats food. In other words, it's got a huge gaping maw. And so when something like the solar wind flies into this aperture, it's really going to just paralyze your detectors. So if you're going to be looking at the solar wind, you don't use a grouper, you need a guppy. And that's exactly what this instrument is here. It's got a really, really small mouth, takes in just a portion of it and says, okay, I've had enough, now go ahead and steer me off of this thing. Because it generally is a very high flux. Next slide. So again, our energy range, 0.17 keV to 33 kV, 128 steps. We get a very high energy resolution, 8%. And again, 5-degree azimuth resolution. Again, that's our designated by our anode pixels. And that allows us to pick up these very fine features in the angular distribution of the solar wind. Again, our geometric factor is rather small compared to many other plasma instruments. But again, this instrument is very, very tiny. The entire sensor would fit in both hands, and it's very light, less than 8 kilograms, including the electronics box. Next slide. So the current state till now, we've already done preliminary testing of the engineering model. We passed critical design review in January of 22, and we're looking at delivering this instrument in December of this year. Admittedly, it's been a really aggressive schedule to get this thing going, but we really have a really, really good crew at Southwest Research, and it's really funny. We used to be, well, we are kind of still Rice heavy. We have another guy by the name of James Webster who's coming through the program. When Dave took me on as a graduate student, I remember him introducing me to Jim Birch and saying, this is the latest member of the Rice Mafia. I felt like I was part of something. And, again, it's this, I love this kind of lineage, this hand down that we have within this department, and I feel utterly privileged to be a member of it. So next slide. So again, we're going to be the primary thermoplasma instrument for NOAA, NASA at L1. The design is based on the ion electron sensor flown on the Rosetta mission, measurement of solar wind ions at Earth L1 to provide early warning of changes which affect our geomagnetic environment. Again, engineering unit is tested, moving to flight instrument build, and we will be delivering that thing in December of 2022. So any questions? I thank you for your time.
Yes, a question right here.
Yes, sir.
You'll be out at L1 during the upcoming Artemis missions then, is that right?
Well, so we'll be out, we're launching in 2025, so yeah.
We're talking about 26 or thereabouts?
But if they ever get up, right, if they keep, they keep scrubbing launches. But no, yes, that would be absolutely right. Yeah, and all the more reason for us to be out there, right? I was going to tell Shannon we got her back, as far as those astronauts going out there, we're going to be making that measurement, so.
That's fantastic data for the missions that are going to be on the moon. That's
yes, sir.
Fantastic. Thank you so much for.
Yes, sir. Thank you.